We've looked at geometric sequences and sort of gained an understanding of what's going on. Today, we're going to be able to calculate the nth term of them. So just a reminder, we've already looked at the nth term of linear sequences, that's sequences that go up by a constant amount. We've also looked at the nth term of quadratic sequences, where the second difference is constant, and actually the first difference between terms is going up by, well, it's a linear sequence. We had a different method for that. Here we've got a different method again. It's I don't know. I don't know where I find this one. I think it's a little bit easier than quadratic sequences to get the nth term. More difficult than the linear sequence, to be honest. There's a little something we can do to help us to get there. So I'll talk about that in a bit. Right, so let's look at 2, 4, 8, 16, 32. How can we get the nth term? Well, if we write it slightly differently, first of all, we recognize we're timesing by 2 every time. Then that essentially means we've got powers of 2. So we could rewrite the sequence as 2, then 2 squared, and then 2 cubed. That's for the third term. The fourth term is 2 to the 4. The fifth term is 2 to the 5. So kind of, you can see that every time it's just 2 to the power of whatever the term number is. Remember, this is term 1, 2, 3, 4, 5. So I want the nth term, term number n, it's going to be 2 to the n, and I've got my nth term. They're going to get more complicated than this, but that is a good starting point. Basically, n is going to always be in the power, because we're timesing by a common multiplier each time. So now I've said that one, can you figure out this one? Pause the video, give it a go. Well, it's going to be really similar. We've got 3 to the power 1. This is actually 3 to the power 2. It helps if you know your powers, obviously. 3 to the power 3. 3 to the power 4 is actually 81. And 3 to the power 5. And the nth term is going to be 3 to the power n. So that seems in a good place. What happens then when we don't just have something to the power of n? Here you can see I'm timesing by 2 each time. But this time it's not quite as simple as just having the powers of 2. There's something else going on. Well, I'm going to explain 2 ways of doing this, and you can decide which you prefer. I'm actually going to, first method is to actually jump in to writing down a general geometric sequence. So we start with some number, a, and then we times through by a common multiplier, in this case r. And then I just keep timesing by that common multiplier. And you can see that the power just goes up. So I can see that A is my first term. I might write that as U1. AR is my second term, U2. This is U3 and U4. So, and U5. So if I want what UN is, I can see it's basically always A to the power of A times R to the power of 1 less than whatever I've got here. So it's going to be a to the r n minus 1. And this, to be honest, if you can remember this is a really good formula to know that you can then apply really quickly to work out the nth term of geometric sequences. So that's method number 1, and let's apply it then. So here, obviously you have to remember what a and r are. So a is the first term. And then r is this multiplier, this constant multiplier. And then n is the nth term. So here I see that a is the first term, it's 6, r is equal to 2, and therefore the nth term, we don't always write u subscript n, I've done that in some places, but I'm just going to go straight for it. It's going to be 6 times, and then 2 to the n minus 1. And I've done it. Okay, I could simplify this, it's got to be said, but I'm not sure. In an exam, you might be expected to simplify it. It's still looking pretty good and is really useful. But we could actually write it as 2 times 3 times 2 to the n minus 1, and I'm multiplying two lots, like two powers of 2, and actually when I times 2 to the n minus 1 by 2, I'm going to get rid of that minus 1. It's just going to actually equal 3 times 2 to the n. That's my answer, as simplified as it can be. And actually we see that now, if we simply take that first sequence and times each term by 3, then we get this one here. So hopefully that makes sense. Method 2 then. I haven't actually left any space here, so I think I'm gonna make a new page. Method 2, let me write it out again. It was 6, 12, 24, 48. I think that's right, because I'm just timesing by 2 every time. Yep, 96. Okay, method 2. I'm going to go through this in a similar way to how I went through linear sequences. So first of all, I recognize that I'm timesing by 2. And so I can see that I've got, for the first term, I might say that I've got something multiplied, or maybe, yeah, something multiplied by one lot of 2. Let's write it like that. When I did linear sequences, I said something plus one lot of 2 or whatever it was. This next one is then going to be something times 2 squared. The third one is going to be something times 2 cubed. And you can see that I've done this now because I always, like the second term has 2 squared in it. The third term has 2 cubed in it. So if I want the nth term, it's going to be something times 2 to the n. And all I need to do is work out what that something is. And I can do that by dividing through by 2, by going this way, dividing through by 2, and that's going to give me 3. And that is going to leave me 3 times 2 to the n. I like both methods. I like this one because it's just a really strong parallel for when you deal with linear sequences. I just want to remind you, when I taught linear sequences, I'm just making one up now, we see that we're adding 4 every time. And so here we've got something plus 1 lot of 4, something plus 2 lots of 4 because I've added 4 on. Here, sorry, I've not left enough space, but here we've got something plus 3 lots of 4. And so the nth term is going to be something plus n lots of 4, or 4n. Let me just explain that again, because I'm adding 4 each time. I'm just increasing this number by 1. And then if I want the something, I have to go this way and minus 4, and that will give me 3. That's the 0th term, and I'm left with 4n plus 3 as my nth term. That's the linear sequence. We're not doing linear sequences here, but I'm just trying to make the comparison. I'm doing essentially the same thing here. It's going to be, I don't say you should just learn this, but it's going to be the multiplier to power n, and then you're going to times by whatever is the 0th term. So 2 methods for working out the nth term of geometric sequences. Decide on one. One of them you end up probably learning a formula that is a to the Rn minus 1, try and understand where that's come from. The second one, you still have to learn a method, that is like you got this approach. Up to you which you use. They're both pretty good, I think. Hopefully, at least one of them makes sense. So let's carry on. Right, if you're feeling confident, then go for it and try and find the nth term of each of these sequences, and I'm going to go through it. I'm trying to decide. I think I might use the a r to the n minus 1 method, at least to start with. I think I'll go through it that way. So I've got that a is 10, and then r is equal to 2. So it's going to be 10 times 2 to the n minus 1. I could, however, simplify that to 5 times 2 times 2 to the n minus 1, and it's going to become 5 times 2 to the n. A bit simpler. Next one, a is 30, and this time r is 3. I'm tripling each time. So it's going to be a times r to the n minus 1. I could, again, simplify it a bit more by writing it as 3 times, so I'm basically finding that 3 goes into this part here and I'm taking it out. And so that's going to become 10 times 3 to the n. That's a pretty solid answer. Next one, a equals 1, r is again equal to 2. So this time it's 1 a times 2 to the n minus 1. In this case, that's my answer. This method really works well here because I just get straight away. That's actually not quite the powers of 2. They've sort of been shifted along. This one here, I'm dividing through by 3, I think, each time, which is equivalent to timesing through by a third. So a is going to be 112. R is equal to a third. So it's going to be 112 times a third. You should put this in a bracket to the power of n minus 1. I don't really like the look of simplifying that, if I'm honest. I think I'm going to leave it like that rather than overcomplicating it. If you've gone through the other method, let me just say, let me just maybe do 1 or 2. So for the other method, remember, I'm saying it's going to be something times 2 to the n, because this is something times 2, something times 2 squared, something times 2 cubed. I want to find that something, so I divide the first term by 2, and I'm going to get my 5 times 2 to the n again. So it works, in a similar kind of way. I don't think we're going to go for any more. I've decided to use this method here. Probably the one I'd go with if I was doing it myself, because I can just, I can derive this formula if I want to, or I can learn it, and it's just very quick to substitute in. There's a bit more going on. So probably this one is winning it out. Right, we can do a few more. Oh no, they're back here. Actually, I say oh no. Surds are great, okay, but it's got to be said, this is where you probably will find it. For GCSE, a geometric sequence, you'll probably get a surd involved. So get ready for them. Right, try this one here. Actually, try all 3. I don't know why I left one blank, but hey, try all 3 of these. Right here, a is equal to 1, r is equal to minus 4. So it's going to be 1 times, now I need that minus 4 in a bracket, n minus 1. And actually, I think that's just the answer. You now leave it inside the bracket. Not much more I can do. That's the answer. For surds, I'm actually timesing by root 2 each time. So a is root 2. R is also equal to root 2. So the nth term is going to be a times r to the n minus 1. And that's actually going to nicely simplify to root 2 to the n. I would leave it like that. Note, you could actually write it as 2 to the half to the n, because the square root of something is the same as raising power of a half. And you could write it as 2 to the n over 2 if you wanted. Probably overcomplicating it with that. Like, I don't mean to confuse you. If you're happy with that, great. Otherwise, hopefully you're happy with this. And now here we go, one with not just a power of a surd, but kind of, maybe we're timesing by a surd, but we've also got other numbers going on in there. Probably, I think actually this one came up previously. We were finding the next term. Probably the best way to find r is to take the third term, because the surd's on top, and divide by the second term, because then you can see these cancel out to 2 root 3. That's going to be my multiplier for all of them, including the first to second. 2 root 3. So a is equal to 4 root 3. R is equal to 2 root 3. The nth term is going to be 4 root 3 multiplied by 2 root 3 all to the power of n minus 1. This method really does work well if you can remember that nth term. Right. Can I simplify it? I can. I can write it as 4 root 3, and then I can actually write it as 2 to the n minus 1 times root 3 to the n minus 1. I can raise them to the power of n minus 1 separately. Why would I want to do that? Because actually, let's see, the root 3 times root 3 to the n minus 1 is going to become root 3 to the n. And then 4 is the same as 2 times 2, so I can actually write it as 2 to the n plus 1. And maybe that's the easiest way of writing it, 2 to the n plus 1. And that's quite a nice way of writing the nth term. I could write it as 2 times 2 root 3 to the n. That's another way of doing it. All of these are, they're decent answers. Okay, hopefully this is all right. So what I'd like to do is, you gave it your best for those. Well done. Try a few more. Okay. I've got several questions, slightly different things going on. Some with surds, some with fractions, and then I've thrown in a couple of what I've called beast questions at the end to test you. And I should say that you do see ones a bit like 1, 2, and 3. Sometimes involving a quadratic sequence. It might be a simple quadratic sequence, but when you have a fraction like this, and actually, I'll just let you have a go at them, and then I'm going to go through it in a minute. So here are the answers. I'm just going to show you the answers to the first one. So these have all been simplified. I think they're simplified as much as possible, really. And then here are the answers to the other ones. So actually, I've purposely made the numerators form a nice sequence and the denominators. If you try and look at the fractions individually, like, how do they link together? Actually, that's going to be a tough problem. But actually, the top is just a linear sequence. It's just 3n minus 1. And the bottom is then actually a geometric sequence. For this one, it's vice versa. The top forms a geometric, the bottom a linear. 2 is probably a little bit easier than 1. And then I've thrown in a quadratic sequence for the numerator and a geometric sequence for the bottom one. This number 4 is, you might be looking at that thinking what, but okay, let's just break it down. The first 3 terms are 2x plus 8. Let's write it as we would normally. Then x minus 1 and then x plus 1. Calculate the 2 possible values of x. So we know it's a geometric sequence, and so we know we are multiplying by the same thing each time, and that's actually the key thing in this question. Because how do we find the multiplier? Well, we do the second term divided by the first term, or the third term divided by the second term. So the multiplier, this question mark, is actually going to equal x minus 1 over 2x plus 8, the second term divided by the first term. But it's also going to equal the third term divided by the second term. And we've got ourselves an equation to solve. Just going to move this out of the way so I've got a bit more space. Again, this is the challenge question, okay? This is going beyond the GCSE, let's be fair. How can we deal with this kind of question? Well, what we can do is we can actually multiply through by each of the denominators. So it's going to become x minus 1, and we're going to multiply by x minus 1, both sides, so it disappears from the right-hand side, and I've got x plus 11. I mean, you could try and do trial and error, but actually that's going to be tough, I think, in this case, times 2x plus 8. So that equation becomes, this, which is now, doesn't look very nice, but it's actually going to create a quadratic. If I multiply out this double bracket, I'm going to get x squared minus 2x plus 1 equals, that doesn't look like a 1, does it? Equals 2x squared plus 8x, I'm expanding brackets quite quickly here, plus 22x plus 88. Right, let's get everything on one side. So I'm going to minus x squared from both sides. So it's going to go from here, and we're going to cancel out that 2. I'm going to add 2x to both sides. So it's going to go from here, and this is going to become, say, 10x. And I'm going to minus 1 from both sides. So this will become 0, and this will become 87. So I'm left with x squared plus 32x plus 87 equals 0. And we've got a quadratic, a large number here, but 87 does have some factors. It doesn't have many factors. And actually, 87 is 3 times 29. Those are its prime factors, actually. So you would only try 1 and 87. Like, so if you're factorizing it, you could put 1 and 87 here. That clearly doesn't add to 32. The only other thing that could work, if it's going to factorize, is 3 and 29. And that does add to give 32. So this is brilliant. So the two possible answers are x equals minus 3 or x equals minus 29. If you wanted, you could substitute them back in just to see what these geometric sequences are. So substituting minus 3, we're going to get 2 minus 4, 8. We're just timesing through by minus 2 every time. Question mark would be minus 2. If I substitute in minus 29, that's going to be a little bit trickier. So minus 20, let me do this on the calculator. 2 times minus 29 plus 8 minus 50. So this is my second one. Minus 50 and then minus 30. And then minus 29 plus 11. I don't know, I'm doing this on the calculator just so I don't make a mistake. Minus 18. So it looks like we're timesing through by 3/5 each time. That's going to be my value for r. Okay, we don't need to do this bit of it, but it's interesting to see. Like, we can check that our answer is correct, I suppose. Last bit, if you're up for it. If you made it so to the end, brilliant. When I introduced geometric sequences, this is what I came up with. Sorry for that slight background noise there. I asked for these possible questions, and I said calculate the number of squares in the next term, and so on. So give this a go. See if you can answer these 4 questions, and then I'll go through it. So number 1, we can see that we're timesing by 5 every time. So it's 625 times 5, which is going to be 3,125, I think. The nth term, actually it's just, well, let's go through it in detail. A is going to be 1, r is going to be 5, and so the nth term is just going to be 1 times 5 to the n minus 1, which we can just write as 5 to the n minus 1. If you want to use this other method that I gave you, then it's going to be question mark times 5 as my first term, question mark times 5 squared as my second term, nth term is going to be question mark times 5 to the n. If I want to know what question mark is, I need to divide by 5, so it's going to be 1/5. It's actually going to be 1/5 times 5 to the n, and that will simplify to 5 to the n minus 1, because it's 5 to the n divided by 5, and I subtract 1 from the power. Is this number in the sequence? Well, probably the best thing to do is let's just try something out. Okay, so we've got something in the sequence and just keep timesing by 5. So that's, wait, let me just, so 5, or even substituting like this, 5 to the 8. Okay, 5 to the 9 is going to be that, yes. So the answer is yes. It is the 9th term. Hold on, it's not the 9th term because it's 5 to the n minus 1. So 5 is going to be the 10th term. 5 to the 10 minus 1 gives me that. It is the 10th term. and calculate the first term that's greater than 20,000. To be honest, you tend to see this sort of question more in A level, but it's not that bad. Again, well, for our case, we can just do trial and error. So we can do, let's do 5 to the power of 6. That's still less. So that's actually the 7th term, because remember it's 5 to the 7 minus 1. Okay, what about the 8th term? That's too much. So it's going to be, oh no, that's it, isn't it? The 8th term. So I should probably write down the smaller one. So the 7th term is 15,625. This is just showing that the 8th term is indeed going to be the first one that's greater than 20,000. There's not one before it that is 78,125. Okay, a good topic, a challenging topic, nth term, especially when you get surds involved. Try and make sure you're happy with one of the methods. You know, even better if you can understand both. Make sure you can deal with surds, involving surds like this, like an F. Be aware, I do see these come up when you get like a quadratic sequence at the top and then maybe a linear or a geometric on the bottom. Good challenge question. Some questions to finish. We've finished geometric sequences for GCSE. Well done.